Yeah, welcome to a section about glycolysis. You certainly learned it in school by heart, but you never understood it. This has to change now. Yeah, honestly, you're not alone. I think most of you have learned glycolysis already in school. But what you did usually is in school, you just learn it by heart. So you have all these names, you have some of the enzymes, you write it down, and 2 minutes after the exam, you have forgotten it. This is of no use because glycolysis is the central catabolic pathway, and it's wise to understand what is happening there, because if you have understood what's happening there, it's way easier to grab all this pathway and to understand also all other catabolic pathways, at least if it's sugar fermentation or whatsoever, because the key principles are already there in glycolysis. So here we go. Yeah, if we talk about glycolysis, of course, we start with glucose. And honestly, glycolysis is a general name for all catabolic pathways of glucose. But this is the Embden-Meyerhof Parnas pathway. It's generally regarded as the glycolysis pathway. So if I talk about glycolysis now, I mean, of course, the Embden-Meyerhof Parnas pathway. So let's start with glucose. So we put a molecule of glucose. So this is the glucose. Now the first step in glycolysis is a phosphorylation of this glucose. And this phosphorylation yields then glucose 6-phosphate. And here we have now our phosphate. So of course this is a phosphate molecule, it's PO4 2-. I just abbreviate it like this, and this is coming not from an inorganic phosphate, this is coming from ATP, and of course then you get here ADP, and this phosphate is being transformed. An enzyme which phosphorylates another molecule is called a kinase. So this molecule must be called kinase, and as it's phosphorylating an hexose, glucose is an hexose, it's called hexokinase. So nothing special is happening, you just phosphorylate at the C6 position, yielding here glucose 6-phosphate. So that's the first step in glycolysis. At the end, what you do here is you save your sugar, because as soon as it's phosphorylated, it's a charged molecule and you cannot lose this molecule anymore by diffusion. You want to keep the sugar in your cell. So now the next step is performed by an enzyme which is called an isomerase. What is an isomerase actually doing? An isomerase more or less shifts keto groups. So if I have a molecule R1 and I have a keto group here, and an isomerase will catalyze the following reaction. And we will end up with this molecule R1. Nothing happens here. We just put the C, the carbons first, R2. And now I have my keto group put at this position, and this is still there. So I have moved my keto group. This is what an isomerase does. It could, of course, move in any direction. So let's remove this. If I do that with glucose 6-phosphate, what I get is fructose 6-phosphate. Okay, and this molecule is called fructose 6-phosphate. In this presentation, you don't really see what this isomerase is doing. So, of course, in solution, sugars are in this closed form. The major part of the sugars are in the closed form. But of course, you can also draw glucose like this. This is what you know. So you could write glucose like this. Of course, you know the rule. Ta, tu, ta, ta. So here are my hydroxyl groups in this projection. An hydroxyl group. And of course, I have my hydrogens also there. And now, so this is again the glucose. And if I have my isomerase now on this molecule, the only C double bond oxygen is here. So this is in my aldehyde group. I move that to the next position. I just put my carbons first. 1, 2, 3, 4, 5, 6. Okay, now I move this group down there, and what I get is a keto group here. I have, of course, then the hydroxyl group needs to go up, and the remaining hydroxyl groups remain at the same position. So this one is here, and if it's phosphate, the only difference is that I have my phosphate here. So phosphate, phosphate, because you count from the reducing group. So this is C1, C2, C3, 4, 5, 6, and therefore the molecule is called glucose 6-phosphate, and in this case, of course, fructose 6-phosphate. And you see what happens with the isomerase is you move this group to this position. So this is what happens with the isomerase. And of course, in this projection, it's easier to see what's really happening with this enzyme. Now from fructose 6-phosphate, we go to the next reaction, which is a kinase. So again, we have a kinase, and this kinase is called phosphofructokinase. And if it's called kinase, it means that you phosphorylate fructose 6-phosphate. You could also call it fructose 6-phosphate kinase. This is the same. So it's the same would be fructose. Also fine with this name. So the kinase stands for what the enzyme is doing, and the surname kind of tells you what is the substrate of the molecule, and it's fructose 6-phosphate. Now, what are you doing if you put a kinase here? Here you simply, again, you phosphorylate. So first of all, let's put the backbone of fructose again. So we have here, again, fructose 6-phosphate. However, we have our kinase, so we have our ATP, which gets into the reaction. And of course, gets out as ADP. It's a kinase, so therefore, this should be the reaction. We had already this phosphate here, and now the next phosphorylation happens at this position, and this is the C1. So what we get is fructose 1,6-bis-phosphate. So at that point, we didn't do very dramatic things. We consumed indeed ATP. So we took energy for these reactions. We produced phosphoesters. These are ester bonds here. So therefore, the energy of these bonds is lower than the energy of the ATP. So these were irreversible reactions. Okay, now we have fructose 1,6-bisphosphate, and now we come to the next step, and this is the aldolase. So the aldolase does the following. The aldolase splits the fructose 1,6-bisphosphate in 2 C3 subunits. And these C3 subunits are, on the one hand, dihydroxyacetone phosphate. So this is dihydroxyacetone phosphate. The other molecule which is produced is glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate. So the enzyme which catalyzes this step is an aldolase, because an aldol is a C3 subunit. So the aldolase splits this fructose into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Now, usually people don't like to learn glycolysis with structure formulas because it makes things so complicated. Of course, with the sugar molecules, to be honest, the positions of these hydroxyl groups, this is something which is not intuitive. You have to learn by heart, more or less. But as soon as the aldolase came into place, things really get easy. So the names look complicated, but if you look at the structure formulas, things what are happening are very easy. And as you look at this, you see that we have now here an aldehyde group and here a keto group. So the only difference between these two molecules is that if you move this aldehyde group to this position, you will end up in this molecule. And what enzyme can perform such a reaction? You know it, an isomerase. So if we put an isomerase here in between, we can convert these two molecules into each other. So the full name is triose phosphate isomerase, but this doesn't matter because it is an isomerase for trioses. At the end, it's an isomerase. That's the important thing. And then we converted it. Now the names look a bit ugly. So on the structure formula, it's very easy because you have this, as I said, we have this aldehyde group, which is shifted from an isomerase to a keto group. Now the names look so problematic. What you did at school is suddenly you learned glycolysis by learning by heart the names, and then of course structure formulas you didn't look at because they are so complicated. But it's the other way around. The structure formulas make your life simple because there is not much going on here, and if you know the structure formulas, it's way easier then to deduce the names based on the structure formulas than the other way around. Now what is glyceraldehyde 3-phosphate and what is dihydroxyacetone phosphate? Now let's just look what is acetone. So acetone is an one. One are always substances with keto groups. So let's just put a keto group. Here we have it. And then we have two methyl groups, adjacent methyl groups, and voila, this is acetone. This is where you get your the color of your nails away. If you have colored your nails, then you use acetone and you put it away. So you use it every day as a solvent. At least most of the girls do it, less the boys. But things change, so it's more and more in use. This is acetone. Now, if I put, instead of this methyl groups here, these two hydroxyl groups, this molecule is called dihydroxyacetone. Why? Because it's dihydroxy and the backbone is called acetone. So that's where the name comes from. So, and this is just then dihydroxyacetone phosphate if I put a phosphate there. Now it's dihydroxyacetone phosphate. So it's very straightforward to come up to this name if you know the structure formula of acetone, which you have learned for sure in organic chemistry. Now, what about the other molecule, glyceraldehyde 3-phosphate? Well, the backbone is this substance here. Also C3, H2, H2, hydroxyl group, hydroxyl group, hydroxyl group. And this is glycerol. So the name comes from originally glycerol. And if we now change this with an aldehyde group here, if we put instead of the hydroxyl group an aldehyde group, this is called glyceraldehyde. So we have the aldehyde inside. So it's just glycerol where we have one hydroxyl group substituted by an aldehyde group. And of course, if we put here a phosphate, then it is glyceraldehyde 3-phosphate because you start counting here. This is C1, always at the reducing group. So the names at the end are very simple. If you see the structure formula and that they derive from substances like glycerol and acetone as a basis, which are basic substances which you're allowed to know, you can deduce easily the structure formula. Now, the next step here, we go from glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. And what we have here now is an oxidation. Indeed, what we do is we oxidize this keto group into a carboxyl group. And this is the central reaction in glycolysis. So what we have here is this group. So wait a second, we will fill it. And we have then here our hydroxyl group. And of course here we still have our phosphate. Now what's happening here, we have oxidized this aldehyde group into a carboxyl group. And at the same time, we have coupled this oxidation to the binding of an inorganic phosphate. So what we put here is we put an inorganic phosphate. So an inorganic phosphate comes in and it's bound at this position. So this phosphate is not coming from an ATP. This phosphate is coming from an inorganic phosphate. But now we had an oxidation, and you have learned that an oxidation cannot happen alone. So you have to couple couple it to another reaction, it's a redox reaction. And you also already know that in a cell, in general, the coupling is done with NADH. So you couple this to the reduction of NAD plus into NADH. So you produce NADH here, and an enzyme which is oxidizing a metabolite is called dehydrogenase. So this enzyme is called dehydrogenase, and then dehydrogenase always oxidizes. A dehydrogenase takes away hydrogen. This means it takes away electrons. And you remember, oxidation is loss of electrons. Oil rig, oxidation is loss of electrons. So if you lose electrons, it means at the same time that you oxidize the substance. And as the metabolite which is oxidized is called glyceraldehyde 3-phosphate, this enzyme is called glyceraldehyde 3-phosphate dehydrogenase. Okay, so now we have generated this molecule here. It comes from glyceraldehyde 3-phosphate, so we still have a phosphorylation at the third position, but it's an oxidized glyceraldehyde. So this molecule is a glycerate. So 8 always is a name for an acid. Aldehyde obviously is a name for an aldehyde. On is a name for a ketone. So this is an 8, so this is glycerate. This is the backbone, and the 8 comes from this carboxyl group. This gives the 8. Still the glycerol backbone. You have your hydroxyl groups there, and this is called 1,3-bis phosphoglycerate. So I have 2 phosphate molecules, 1,3-bis phospho, and the backbone is glycerate. You see, however, based on the structure formula, what happened is I have an oxidation of my aldehyde group into a carboxyl group. And at the same time, I had a coupling of an inorganic phosphate to this carboxyl group. And you remember what that is. This is a phosphoanhydride. Phosphoanhydride, because it's an acid-acid bond. This here is a phosphoester. And this is very important because the difference between a phosphoanhydride and a phosphoester bond is that an ester bond has a low energy content and a phosphoanhydride has a high energy content. And this energy content is usually so high that you can use this energy to transfer this phosphate onto ATP. And as you remember, this is called substrate level phosphorylation. And exactly that's what the intention was. We wanted to generate such an energy-rich bond here. And with this energy-rich bond, now we can do what we at the end want to do in this catabolic process. We want to generate ATP. That's our intention. So let's do it. Let's generate ATP. In the next step, we have the production of ATP. We, of course, can only use this phosphate because that has high enough energy. So our ADP gets in, and I have an ATP. Now let's mark this in green, that you see that this is from the phosphate at the C1. Of course, you have 3 phosphates, so it's 2 phosphates are coming from the ADP. And now we have the next molecule. What we have is simply the backbone. In cellular conditions, this might be deprotonated, but we don't care. And we have now the same molecule as before, but at C1 we have no more phosphate. We have now 3-phosphoglycerate. So the backbone is the same. It's still glycerate, but in this case, we have just the phosphorylation left at the 3 position. Now, how is the enzyme called? Calculizing this step, this enzyme is called according to the back reaction. So you can also, this often happens. So the back reaction, if you go in this direction, it would of course be a phosphorylation. And many reactions, what we have seen here, are reversible. So you can go also in the other direction. And then this would be called a kinase, coming from the back reaction. And as if it's the back reaction, then the substrate would be, of course, 3-phosphoglycerate. So you can also call it either phosphoglycerol kinase, but you can, of course, also call it 3-phosphoglycerate kinase. Yeah, this is also called phosphoglycerol kinase, but that doesn't matter. Now we have 3-phosphoglycerate, and now you see the enzymes we had at that point with respect to the function are kinases. We have several phosphorylation reactions, at least in the forward or reverse reaction. We have then an aldolase. This is the enzyme which splits it. So the splitting is an exclusive reaction. And we have isomerases, moving keto groups. And finally, we have a dehydrogenase, which catalyzes a oxidation. That's it. So the complexity is low in this case, as you only need to remember what is a kinase catalyzing for a reaction, what is an isomerase catalyzing as a reaction, what is an aldolase catalyzing for a reaction, and what is a dehydrogenase catalyzing for the reaction. If you know what reaction type is catalyzed, it's easy to deduce then these names. So we are at 3-phosphoglycerate. And now we have still one phosphate left. So this phosphate here, our problem is that this phosphate came in with an ATP. So of course, if we would simply hydrolyze now this phosphate, this energy would be gone. We want to produce energy, and net at that point we wouldn't produce energy. So we need to bring this phosphate back onto an ATP molecule. However, unfortunately, if we do that directly from here, it doesn't work because it's an ester bond, and this ester bond doesn't have enough energy. So therefore, we must bring this phosphate in this molecule to a position where the bondage has enough energy in order to be transferred. And in this case, this is done with internal rearrangement, so it's no more an oxidation. The oxidation, again, you remember, happened here. In this case, it's an internal rearrangement. So now the next step is that we bring this phosphate from here to here, so to the hydroxyl group at the C2 position, and this is then catalyzed by an enzyme which is called mutase. So this is a mutase. It has nothing to do with mutation. It is simply bringing this phosphate to a different position. Of course, as it's 3-phosphoglycerate, which is the substrate, this is then a 3-phosphoglycerate mutate or a phosphoglycerol mutase. But we don't care now about the name too much. So at the end, again, what we bring up is this phosphate. So of course here nothing changes. Now we have here the phosphate. I just finish here the remaining molecule. It's here, now the phosphate. And this molecule is then, believe it or not, called 2-phosphoglycerate, because we have moved the phosphate from C3 to C2. Okay, now an enzyme comes into play which is called enolase. Now we have an enolase, and as the name says, the enolase forms an enol. This is certainly a special reaction which you won't see very often in metabolic pathways, but in glycolysis this is also a central reaction. So we are then producing an enol, and an enol means that we have an ene, which is a double bond, and an hydroxyl group at that position. So this is here. And as this is at this position, we have our phosphate. So this is then, of course, still there. So this substance is called phosphoenol pyruvate. This is, of course, a name you should learn by heart. Now, the next step is, if you look at this, this is not an anhydride bond. This is an ester bond. But I have told you that this is still energy rich because we have this keto-enol tautomery where we have the spontaneous rearrangement to the keto group. And by this, the energy of this bond is still high. And therefore, we can use this energy from this bond to transfer the phosphate to ATP. So let's do it. So what we do now is we give the phosphate to ATP, so we produce ATP, ADP to ATP. At the C1 nothing happens, we still have our carboxyl group. Now here, as I said, we have a ketoenotautomerase. So instead of a double bond here, this ene, we have a keto group which is formed. And of course I have a single band here. But now, as this is a double bond, this here is a methyl group. So it's not an oxidation. This is not a redox reaction. It's an internal rearrangement. And this internal rearrangement gives you the energy of this bondage, and therefore you can do this transfer. The molecule what you have produced here is pyruvate, which is the starting point for 99% of all your fermentation reactions. Yeah. Now, the enzyme catalyzing this step is also called with the reverse reaction. The reverse reaction is, of course, then a phosphorylation. So this is pyruvate kinase. So the name comes from the reverse reaction. Interestingly, this is an irreversible reaction, so the reverse reaction cannot happen. So this enzyme has been named about a reaction which cannot happen, but nevertheless, that makes our life easier, because otherwise the name would be very complicated. So we know, well, the kinase catalyzes the phosphorylation. The reverse reaction is, of course, then a generation of ATP. It's not a dephosphorylation, it's a generation of ATP, the reverse reaction of a kinase, and therefore we can easily call it like that. So this is how the glycolysis ends then at our pyruvate. And now let's count what we have produced net. So if we oversee now the complete reaction, what you realize is we have brought in an ATP here, we have brought in a second ATP here, and here we have generated an ATP, here we have generated an ATP. So at the end, this would say 2 ATPs in, 2 ATPs out. We have not gained anything. However, in reality, we have generated 2 molecules here. So, and of course, as we can convert these 2 molecules with the isomerase, we have generated, in principle, 2 molecules of glyceraldehyde 3-phosphate, twofold. So we can generate 2 molecules of 1,3-bisphosphoglycerol. We can generate 2 molecules of 3-phosphoglycerate. This also means that we have generated 2 ATPs here. We have generated 2 NADPHs here. Of course, then this is also twofold here. Yeah. We have generated 2 molecules of 2-phosphoglycerate, and we have generated 2 molecules phosphoenolopyruvate, pyruvate, of course, and here also 2 ATPs. So we have brought in total 1 ATP here, 1 ATP there. So we have brought in 2 ATPs, and we got out 2 ATPs here and 2 ATPs there. So we got out 4 ATPs. So net we have produced 2 ATPs via substrate level phosphorylation. And remember, that's what we wanted. Our intention is produce ATP via substrate level for phosphorylation. So the net reaction is we have glucose plus 2 ADPs plus 2 NAD plus, don't forget that, 2 NAD plus 2 inorganic phosphates gives 2 molecules of pyruvate plus 2 ATPs plus 2 NADH. So, in other words, with our glycolysis reaction, we have produced 2 molecules of pyruvates and 2 molecules of ATP. So we have conserved the energy. So we had an oxidation step. We had exactly one oxidation step. This is the oxidation. And this is the only oxidation step here. And in this oxidation step, as it's a redox reaction, it needs to be coupled. We at the same time produced, of course, our NADH. So we have at the same time production of NADH. So this oxidation is, of course, used to bring in energy in the system. However, the energy which is produced by the oxidation is conserved at the same time by coupling this energy to the phosphate addition. So at the end, what you do here, you partially burn your glucose. But you burn it in a way that you have defined conditions, and that you have conditions that you can conserve the energy from this oxidation via transfer, via production of ATP. Because if you could of course also generate very much simpler pathways from glucose to pyruvate. However, if you would do that in a couple of the, let's say, most simplest way possible, and you don't do all this conversion here, for example, you will lose the energy because you cannot transfer it to ATP, and you will simply produce then heat instead of ATP. The cell doesn't want to produce heat. The cell wants to produce ATP. So why is this reaction so complex on the first side? It is in order that you are able to produce your ATP and conserve the energy. So this is the secret about glycolysis. You produce ATP, you produce 2 molecules of ATP via substrate level phosphorylation. So it's directly coming from energy-rich phosphate bonds. And all the intention here is generate these energy-rich phosphate bonds in order that you have the chance to transfer the energy, for example, from this oxidation step onto ATP. Yeah, this is glycolysis. So welcome in the club. Now you have understood it. It's, again, it is on the first notion, it looks complicated. To be fair, these sugar things are not so overwhelming, because all these hydroxyl groups and positions and so on are quite boring. But the fun part starts here. So when you start here, you can deduce all the names of the molecules from the simple substances. At the end, we talk about acetone and glyceraldehyde, which becomes to glycerate. Yeah? And only after here we start with, again, another name, which is phosphoenol pyruvate, and at the end, pyruvate. Of course, glycolysis is a central pathway. Of course, you know this pathway. That's clear. However, I am not interested that you know the pathway on the first side by heart and forget it one day after the exam. I want you not just to know it, I want you to understand it, because you understood what is a kinase doing, what is an isomerase doing, what is a dehydrogenase doing. So therefore, you can apply your knowledge also to a new pathway which has completely different molecules. But as you know, if I have a molecule with an aldehyde group and I have an oxidation, I will end up in a carboxyl group, regardless of what we have here. Doesn't matter. Yeah, this is the oxidation. If I oxidize this aldehyde group, it will be a hydroxyl group at the end. This is what you know. And if you have then the name of this enzyme will be a dehydrogenase. That's it. So, and if I put a phosphate on a molecule from ATP, this will be a kinase. This could also be named from the reverse reaction. If you just shift keto groups, it's an isomerase. And therefore, of course, this reaction is here an isomerase, and this reaction is an isomerase. In the sugar reaction, it's a bit difficult to see because the sugars are closed. In the open form, it's easier. But in this reaction, it's very clear that the isomerase simply puts this group down there. So therefore, it's an isomerase. So if you know this, and if you learn glycolysis based on the structure formulas, it is way easier to understand, first of all. Second, it helps you more. It's more sustainable because it stays in your brain. And third, if you just learn it by heart for the exam in Applied Microbiology, it's of no use for you because you will not have questions directly on glycolysis. You need to know it anyhow. You will know it if you know all the reactions and so on, but you will be asked questions about adapting that. Now, an important question is always, do I need to memorize all these structure formulas? The sad story is yes. Of course, you need to know these structure formulas. You need to know the structure formula of glucose. You need to know the structure formula of fructose. That's basic. You need to know, of course, the structure formula of dihydroxyacetone phosphate. However, it's easy because I said, if you know how acetone looks like, it's easy to deduce this dihydroxyacetone phosphate. You need to know glyceraldehyde 3-phosphate, how it looks like. The key reaction in glycolysis, remember, is this reaction here. This is the key reaction. These are your friends in this reaction. So if you wake up at midnight and somebody says, write down the key reaction, of course you know it by heart because it's deeply burnt into your brain. You can draw the molecules of glyceraldehyde 3-phosphate and the molecules of 1,3-bisphosphoglycerate. Of course you know that the next step, if somebody asks you, now I have a transfer of the phosphate to ADP, you know this can only come from the PC1 position because this is a phosphoanhydride bond. You know that. Therefore, you don't need to learn by heart these other molecules here because you can deduce that. You need to know by heart phosphoenolopyruvate is a key molecule. And of course, you also need to know by heart pyruvate. So, but if you learn based on the structure formulas, you know it anyhow. That makes life simpler. So welcome to the club. You're now experts in glycolysis. You're experts in metabolism because if you have completely understood glycolysis, the Meyerhof Parnas pathway to be more precise, these principles of this pathway you will find in many, many other fermentation pathways, as long as we talk about carbohydrate fermentation pathways. And that's cool. So if you really know this, then all the other pathways will be easy, promised. And now, thank you very much for your attention and enjoy being in the club, understanders of glycolysis. Bye.